So this is actually before going into this NP complete problems, let us just try to recollect what type of problems we studied so far. So we have studied so many algorithms here, and we have computed the time complexity. Actually, all most of these algorithms are okay. So most of these algorithms are time complexity, or we can say that they are polynomial time algorithms, which means their worst case time complexity can be denoted as big of n power k for some constant k. So their worst case running time can be represented as big of n power k for some constant k. So next question is whether all the problems can be solved in polynomial time. Okay, so the answer is no. There are some problems which cannot be solved in polynomial time. One famous problem is that is familiar to you is the halting problem of a Turing machine. Okay, Turing machine's halting problem. And you have studied that this cannot be solved by any computer, no matter how much time is provided. Okay, so what is Turing machine's halting problem? So given an input string, you cannot tell, or you are not able to write an algorithm to decide whether this Turing machine will halt or not. Okay, so given a Turing machine and given one input string, suppose the string is accepted by the Turing machine, what happens? After some moves, the Turing machine will halt. That is for sure. But if the string is not accepted by the Turing machine, then what happens? We cannot say that whether the Turing machine will halt after some moments or not. Okay, sometimes the Turing machine will enter into an infinite loop. Okay, so that problem is known as Turing machine's halting problem. Uh, I think you have studied it in TOC, and we can say that, or we can yes, we can say that this halting problem cannot be solved in polynomial time, which means that that cannot be solved by any computer. Okay, no matter how much time is provided. Maybe uh, you give as much time as required, but this you won't be able to write an algorithm for that. Okay, and there are also problems that can be solved. Okay, and that is the case with the halting problem. But there are some problems which can be solved. Okay, there are some problems we saw that some problems can be solved in polynomial time, and some problems, even though you give some exponential time or more than that, you won't be able to solve that. Just like a Turing machine solving problem. And there are some problems that can be solved, but not in polynomial time. Okay, but not in big of n for k for any constant k. Okay. Generally, we think of problems that are solvable by polynomial time algorithms as being tractable problems or easy problems. Okay. And problems that require super polynomial time as being intractable problems, okay, or hard problems. So we can say that there are tractable problems, so which means that require polynomial time for solving it. That is tractable problems, or we can say that polynomial time means it is actually an easy algorithm. Okay, and the problems that require super polynomial time are intractable problems, or they're hard problems. It is very difficult to solve, or sometimes it is not possible to solve. Okay, so no polynomial time algorithm has it been discovered for an NP complete. There is another class. Anyway, we'll discuss or we'll define this term NP complete problem. But before that, we do not know polynomial algorithm for an NP-complete problem. Okay, nor has anyone yet been able to prove that no polynomial time algorithm can exist for any one of them. Okay, so it is actually uh, we can say that it is okay. So we can say that no polynomial time algorithm has been discovered yet. Okay. Or maybe there is no such algorithm exists. Okay. Maybe no one is able to write such algorithms for some particular problems. Okay. So they are actually NP complete problems. They are very hard problems. Okay. And one more interesting question is that whether P or P not equal to NP. Okay, P not equal to NP. Actually, P is for the polynomial time solvable algorithms or problems. That is, you can call them as class P problems. Class P contains all the problems. It is actually class means it is actually set. Okay. Okay. This is actually a set of all problems which can be solved in polynomial time. That is the class P. And there is another class that is NP, that is non-polynomial. NP, that is non-polynomial. So which means set of problems that cannot be solved in what do you say, NP. Sorry, polynomial here, but that definition is not exact. Okay, that is not accurate. Actually, NP problems are the problems uh, which can be verified in polynomial time. That is more accurate. Okay. Which can we'll see the definition what is meant by verifiability and all this. But time being, it is actually non-polynomial time algorithms, which means maybe that can be verified in polynomial time. Of course, that cannot be solved in polynomial time, but that can be verified in polynomial time. That is the class NP. We will see that, and whether P equal to NP, okay, or P not equal to NP. It is actually an open question uh, till now. Researchers are trying to find out whether P is equal to NP. Okay. P is actually the set of problems that can be solved in polynomial time, and NP is the set of problems that can be uh, verified in polynomial time. Okay, or that can it is not accurate to say that it cannot be solved in polynomial time. Anyway, that is what to say. NP is the problems that can be verified in polynomial time. Okay. So we can say that P is actually a subset of NP. That is a more accurate thing. P is a subset of NP because any problem that can be solved in polynomial time can be verified in polynomial time. So obviously P is in any problem P that is in NP. So P is actually a subset of NP, but P whether P is equal to NP. NP is actually a wide class of problems which can be solved in polynomial time. It is not saying anything about the complexity of the algorithm, or it is not saying about whether that can be solved in polynomial time. It only says that it can be verified in polynomial time. And uh, most of the security algorithms are built on this concept. That is, there exist NP complete problems or very hard problems. Okay, that's how most of the security is set up. And if you prove that P is equal to NP, okay, if you prove that P is equal to NP, then all the security will not be there. Okay, because which means the security algorithm is based on the concept that that is very difficult to break. Okay, that is maybe impossible to break. So, and if you prove that P is equal to NP, that is something like a polynomial time, then you will be able to break that algorithm. So, which means the security will not be there. So P is equal to NK is actually very dangerous. If at all if somebody tries to prove that P is equal to NP, then he will be able to get all the money from the world because all the security has gone, and he will get all the money. That is the case with P is equal to NP. And this question actually arose in 1971. This is still an open question. And one aspect of this NP-complete problem is that several of them seem on the surface to be similar to problems that are polynomial time algorithms. Okay, so that what we said. Several of them seem on the surface to be similar to problems, and in the case of NP-complete problems, several of them seem on the surface to be similar to problems that are polynomial time algorithms. We can feel that, or we think that it is similar to polynomial time algorithms. Actually, NP-complete problems are mostly for decision problems. Okay, we are by NP-complete problems we mean that they are actually decision problems. Okay, so just a decision problem. Given a Turing machine, and given an question whether the Turing machine will halt or not. That is actually a decision problem because its output is two conditions, which means you should decide that condition whether it will halt or not halt. So that is yes or no will be the answer. Such problems are known as decision problems. So you will have a different variant of that problem, that is a polynomial that you can for which you can write a polynomial time algorithm. And when we discuss the next pair of problems, we are going to discuss. One is a polynomial time algorithm, solvable in polynomial time, and another one is an NP-complete problem. Okay. So let us see what is meant by that. Shortest versus longest simple paths. Then Euler 2 versus Hamiltonian cycle. Hamiltonian cycle of the number of പഠിച്ചിട്ടുണ്ട്. നമ്മുടെ GTC-നകത്ത് പഠിച്ചിട്ടുണ്ട്. അതുകൂടാതെ let us see. So shortest versus longest as simple paths. So even with negative edge weights, we can find shortest paths. So we have found out some algorithms for that, for finding out the shortest path from a single source in a directed graph G equal to V comma I in big of V E type. The V is the number of vertices and E is number of edges. And finding a longest path between two vertices is difficult. But finding longest simple path between two vertices is actually difficult. Merely determining whether a graph contains a simple path with at least a given number of edges is NP-complete. That makes it complex. Okay, so we are asked to find out, or we are asked to determine whether a graph contains a simple path with at least a given number of edges. Okay, that makes it very difficult. That is actually an NP-complete problem. So we'll see some examples. Then Euler 2 versus Hamiltonian cycle. And Euler 2 of a connected graph, that you know very well, that is actually a cycle um, that traverses each edge of G exactly once. Okay, although it may visit a vertex more than once. We can determine whether a graph has an Euler 2 in only big of E type. E is the number of edges. And in fact, we can find the edges of the 2 in big of E type. Okay, that is clear. So we can find out an Euler 2 in a graph. But a Hamiltonian cycle of a directed graph G, that is actually a simple cycle that contains each vertex in D. It should contain all the vertices in D. And determining whether a directed graph has a Hamiltonian cycle is actually NP-complete. Okay, so determining whether a directed graph has a Hamiltonian cycle is NP-complete. Then another problem is satisfiability problem. Okay, have you heard about the satisfiability problem? It is a very famous problem. So satisfiability problem is given a Boolean expression. So we know what is a Boolean expression, a Boolean formula that contains actually variables and they are connected by the conjunctions or disjunctions. Okay, so the Boolean variables are known as literals. Okay, and these Boolean variable, which means they can take only two values, either 0 or 1. And we have connectives like this and, or, and no, and parenthesis for this grouping. So that is actually a Boolean, what do you say, Boolean expression or Boolean formula. A Boolean formula is satisfiable if there is some assignment of the value 0 and 1 to its variables that causes equivalue to 1. Okay. So we have a Boolean expression or Boolean formula with n variables or n literals. So we are checking whether this Boolean expression is satisfiable or not. Okay. So how can we check whether this is satisfiable? Satisfiable means given a truth assignments to variables or literals in the Boolean expression, whether the truth value of this or truth value of the entire Boolean expression is true. Yeah, that is meant by satisfiable. Then we can say that the expression is satisfiable. Otherwise, it is not satisfiable. Okay. So whether, which means we have n literals in the Boolean expression, we can non-deterministically thus value 0 or 1 to each of these literals, and we'll evaluate this expression, and suppose we get a true value or a 1 value after this, then that means this Boolean expression is satisfiable for corresponding to this truth assignment. Okay, truth assignment to a Boolean expression means values given to this literals of this, what do you say, literals of this Boolean expression. Okay, so when the whole expression evaluates to true, it means that the Boolean expression is satisfiable. Otherwise, it is not satisfiable. Okay, clear. Boolean expression is satisfiable or not satisfiable. So satisfiability problem is that given a Boolean expression, okay, given a Boolean expression, whether this one is satisfiable or not. Okay, again it is a decision problem. So we need to decide whether this Boolean expression is satisfiable or not. Okay, that is known as a decision problem, and that problem is known as a satisfiability problem. And actually, this satisfiability problem is a very hard problem. How do you say that the satisfiability problem is very hard? Hard problem. Okay. So which means this when what you can do about this is that suppose you have n literals in your Boolean expression, n literals are there, then how will you solve this n literals? Or how will you find the truth values? Okay, so only possibility is that you can non-deterministically guess values for this literals. Okay, the first literal is given 0, second literal is given 1, etc. I'll assume some values, okay, for all these literals, and I will evaluate. Okay, and if that is not true, then I will take another combination, etc. So I will exhaustively search or check all the possibilities. Then I can say that if for all these possibilities the expression evaluates to false, means that is not satisfiable. Otherwise it is. If at least one truth assignment I can give, then I can say that the Boolean expression is satisfiable. Okay, so that is a satisfiability problem. And when we take all the possibilities, okay, so that makes it very hard problem, and we can say that this is actually an NP-complete problem. Anyway, we are going to define NP-completeness later. So this is actually an NP-complete problem. So here, actually from this Boolean expression, or our famous halting problem, that is Turing machine halting problem, can be reduced to this Boolean expression or satisfiability problem. There is a reduction process for that. That is actually not included in your syllabus, I think. I don't know. That is very simple. That step is very simple. And there are two, you know about conjunctive normal forms. Okay, conjunctive normal form. You heard about conjunctive normal form. Again, we are talking about Boolean expressions. conjunctive normal form means it is actually a conjunction of clauses, okay, or conjunction of disjuncts, both are same. So conjunction of clause, what is meant by a clause? A clause, when we talk about these Boolean expressions, we always hear the term, this clauses. Okay, a clause means it is actually a disjunction of literals. So when we talk about a Boolean expression, the Boolean expression contains this Boolean variables, and the Boolean variable is known as a literal. Okay, you can say either Boolean variable or literal, both are same. So this clause means it is actually a disjunction of this literals. Okay, disjunction means that is or. Okay, or of this literals. Suppose you have three literals x1, x2, and x3, and you can say that x1 or x2 or x3. That is actually a clause because it is a disjunction of literals, disjunction of three literals. Okay, and a conjunctive normal form means CNF. That means it is conjunction of this process or conjunction of this disjuncts. Okay, conjunction means again you are taking logical and. So suppose you have x1 and x1 or x2 or x3. Okay, so x1 or x2 or x3 is a clause, and again suppose x4 is there, x4 you can consider as another clause. So x1 or x2 or x3 or x3. Okay, then and x4, that is a um, conjunction of this distance, and you can say that conjunctive normal form has many types. One is a 2 CNF, another one is a 3 CNF. Okay, so 2 CNF means, and they have a definition for that. Okay, so or in general, we can say that it is a K conjunctive normal form. If each of this process has K distinct literals. Okay, if each of this clauses has k literals, then it is known as a k conjunctive normal form. That is KCNF if it is the AND of process of ORs of exactly k variables or their negations. So this one, consider this Boolean expression x1 or negation x2 and x1 negation x1 or x3 and negation x2 or negation x3. So this is inside this parenthesis you have disjuncts. So two literals. This is known as a clause. So this is uh, disjuncts of two literals x1 or x2. So each of this clause has exactly two literal, okay, distinct literals. Okay, that is known as a 2 CNF. If each of this clauses has a three literals, then you can say that it is a 3 CNF, etc. Okay, so it has a suppose this has a satisfying assignment x1 equal to 1, x2 equal to 0, x3 equal to 1. There is a polynomial time algorithm to determine whether a 2 CNF formula is satisfiable, determining whether a 3 CNF formula is satisfiable as NP complete. Actually, we have a polynomial time algorithm to determine. You can find out this polynomial time algorithm. Okay, so you can determine this polynomial time algorithm. Uh, Sorry, you can find out that polynomial time algorithm to determine whether a 2 CNF is satisfied. What makes it simple is that it has only two literals. Inside each clause, it has only two literals. So that is actually simple one. You can choose different combinations and you can make some assumptions on that. You can make some rules of this Boolean expressions on that, and you that is actually solvable in polynomial type 2 CNF. But 3 CNF is actually not satisfied, whether it is satisfied or not. That is a very hard problem to solve. That is known as it is NP complete. It is an NP complete problem. Okay. So here NP completeness and the classes P and NP. The class, all these definitions can come in anyway. The class P consists of those problems that are solvable in polynomial time. There are problems that can be solved in time big of n power k for some constant k, where n is the size of the input to the problem. Most of the problems examined in previous modules are in P. Okay, the class. Most of the problems means we have this traveling salesman's problem and all this. All these are actually that will take exponential time. N square into 2 power n, that is traveling salesman's problem. Anyway, the class NP consists of those problems that are verifiable in polynomial time. Okay, so what is meant by verifiability is that we haven't called it. What is meant by verifying a problem? So we are saying that particular problems can be solved in polynomial time, okay, or some problems can be verified in polynomial time. By solving a problem, it means that we are able to come with a solution. Okay, okay, this is the solution for this particular problem. And what is meant by what do you say, verifiability? So we are not solving the problem as such, but suppose somehow we get a certificate or a possible solution. Okay, somebody somehow give me a possible solution, that is known as a certificate. Okay, okay. For example, in the case of a traveling salesman's problem, suppose somebody gives me a tool. Okay, then or in the case of a minimum cost spanning tree, so if somebody gives me a minimum or a spanning tree and its cost, I can check whether that is a minimum cost. I can verify this one. Okay, that is a case, which means suppose I get a solution or a certificate of a solution, then we could verify that the certificate is correct in time polynomial in the size of the input to the problem. Okay, suppose I have a Hamiltonian cycle problem given a directed graph G. A certificate would be a sequence V1 to actually this applies to this kind of problems. Okay, what do you say? A certificate would be a sequence in the case of a Hamiltonian cycle problem. Certificate would be a sequence. What is a Hamiltonian cycle? It is actually a cycle, which means it starts and ends at the same vertex, and it should contain all the vertices in the graph. Okay, that is a condition. It should contain all the vertices in the graph. So a certificate, a possible certificate will be a sequence like V12, for example, V. This V means that is size of this or number of vertices in the graph. So V12 VB, or I can say V12 VN, where there are n vertices in the graph. Then that is actually a possible solution. And this is order V1, V2, V3. Okay, I should get a sequence. This is a sequence, which means V1 first, then V2, V3, etc. So I give you an order or a certificate. Then it is very easy to check in polynomial time. Okay, so I can check this in polynomial time, that whether this one is a Hamiltonian cycle or not. How can I check that? I should check whether there is an edge between each pair of vertices in this sequence. Okay, so which means I can verify that in Vi comma Vi plus 1 is element of P. For I is equal to 1, 2, 3, etc. V minus 1. And that V comma V1 element of E as well. Okay, so for each I, what I need to check is that Vi comma Vi plus 1 is element of E. That I can check in the in polynomial time, because if there are n vertices, then it will take big of n time only. Okay, so Vi comma Vi plus 1 is element of n. That is checked, and the last one is that we should take BB, that is the last vertex, comma B1. There should be an edge from the last vertex to the first vertex. That should also be checked. So, given, suppose somehow I get a solution or a certificate. If some algorithm is there that will give me a certificate, then I can verify whether this is a Hamiltonian cycle or not. I can come up with a solution. Given a certificate, I will be able to verify whether this is a Hamiltonian cycle or not. And that can be done in polynomial. Okay. And again, in the case of a 3CNF satisfiability problem, a certificate would be, what is a certificate there? An assignment of values to variables. Okay. An assignment of values to variables. So I have, for example, I have n literals in that 3CNF. Then I can come up with values for each of these literals based on in which clause they appear, and so and so. So in that order, I can give you a certificate. Certificate would be a sequence, and if I substitute the values in the original problem, then I can verify that this will be the value of this Boolean expression is true or not. Okay, and I can do that in polynomial time, because why I can say that that can be done in polynomial time, because there is only polynomial number of vertices, variables in the Boolean expression. Okay, maybe n is the number of literals in the Boolean expression. So I can substitute each of these variables or literals, and I can verify whether it is true or not.